We are now recording. Can everyone see slides online?
Yes.
Yeah.
Perfect. You see one slide, chapter 1, bonding and structure.
Correct.
Not even sure. Okay, I do need to fix this sound before we get any further. I apologize. That should just take a second. Speaker. Speaker's off.
Do you have maybe more than one Teams page open?
I don't think. I think maybe I'm still in on my iPad. Let's get out of here. Hang up. Okay. Yay.
Awesome.
All right. Now, is anyone here in the classroom in on Teams as well, by any chance? Just if you could just give me like a thumbs up that what you're seeing here is exactly what people online are seeing as well. Then we could finally get started. 10 minutes in. I got to figure out why. So my plan was in giving this class is I have my iPad because we don't really have easy access to chalkboards. Like we have whiteboards all up around the classroom. The problem with that is people online can't see what's on the boards, which is no fun. But I have an iPad which I can draw on, which comes up here, which everyone online can see. I tested it and it worked great. Just today, for some reason, every time I open QuickTime, which is what I need to make it work, QuickTime crashes. So I restarted my computer, still crashed every time. So I'm not sure what's going on there, but hopefully I'll get that fixed before Friday. So welcome. This is going to be a very weird semester, but hopefully quite good. My plan is for the first 2 units to be going through, the first 2 classes to go through the first unit, and it'll be pretty quick. The first unit is mostly review, and the stuff from first year that's most important for you guys to know and be reviewing are things around Lewis structures, around molecular shapes, around that kind of stuff. And I'm not sure if you guys know, have looked yet, but I put that tutorial up online about how to draw Lewis structures. So if you're a little fuzzy on how that is supposed to work, please go online and please go through that tutorial and make sure you're good with that. There's a PDF version of essentially the same thing online as well. So if you don't want to watch me go through every gruesome detail and you want to do it yourself, you can do that more quickly if you like, all on your own. Are we good with Teams? I had to turn off my mic or my speakers here from Teams because it's giving me brutal feedback. So, guy at the back, you're in Teams?
I'm struggling to connect to our meeting.
Oh. Okay. Well, if anyone else is in Teams and can make sure that this is working well for everybody on Teams as well, that would be fantastic. So just some general things about organic chemistry, about this course that I want to kind of emphasize right at the beginning, make sure everyone's sort of upfront and clear about these things, is that organic chemistry is going to be very different from any chemistry course you've taken before. Okay, we've got a thumbs up in the back. It's going to be very different from any chemistry course you've taken before in that, first of all, you're barely going to be using math. Okay, there's essentially 0 math in this organic chemistry course. And as such, it's going to be much more focused on the structural aspects of chemistry that we talked about a little bit in first year. I kind of have a picture up here of a chessboard, people playing chess. And I kind of view being good at organic chemistry a little like it is being good at chess. And that if you wanted to be good at chess, I mean, the first thing is you have to know all the rules. You have to know how the pieces move. You know, you have to know what's possible. And that's really what I think is like in chemistry, learning Lewis structures. Okay, those are the rules that we're going to be using. Okay, once you know those, it doesn't mean you're good at chemistry if you just know the rules, just know how to make Lewis structures, but you have to be good at that to get to the next step. The other thing about chess is a terrible way to get good at chess is to watch professionals play 50 games and memorize the pattern of moves they make, right? Because if that's all you've done, if you've memorized 50 games, say, and then you walk into a new game and what you see isn't one of those 50 games that you've memorized, you have absolutely nothing to go on. And organic chemistry is a little bit like that. Memorizing some of the examples that I show you is really not going to be super useful, because what's going to be super important is not just memorizing those particular things, but being able to understand why you're doing a certain thing at a certain point in time. So that requires a lot of practice. It's not something you can really cram for. And this probably doesn't make any sense to anybody right now, but this hopefully becomes more clear as the semester goes. Don't try to rely on memorization to become good at this course. Okay, so we're going to go through some basics. This is some stuff from first year that you guys need to know. I'm going to refresh this just a little bit. Structure of the atom, probably something you started learning back in, I don't know, grade 5 or something. Atoms have a nucleus in the center. They have electrons outside. And a good chunk of our first year course is dedicated to teaching you guys how these electrons are structured, okay? How they exist. They exist in regions of space that we call orbitals. Orbitals come in different shapes and sizes and energies. First of all, we say they are organized into shells. And we give them a principal quantum number of n, where the lower the number of n, the lower the energy, and the smaller that shell is. So you can see in this picture of the periodic table, elements that are in the first row, they have their outermost electrons in the n equals 1 shell. If you're in the second row, n equals 2 shell, n equals 3 shell, so on, so on, so on. Also, the orbitals, I mean, within one shell, you can have orbitals with different shapes. Okay, and these shapes, for the first 2 rows at least, are only 2 possibilities. There's S shapes, which are spherical, and there's P shapes, which are kind of like dumbbell shaped. There's a lobe on the top and a lobe on the bottom. We'll be looking at those a little bit too. The reason I kind of can block off this top row, 2 rows of elements, is these are the elements we're going to be most concerned with in organic chemistry. Okay, there's a lot of very interesting stuff that happens over there in the D block and the transition metals, and we have a course about that if you're interested in the chemistry of those elements. But in organic chemistry, it's mostly the first 2 rows, and there's a few additional elements. Carbon, most centrally in organic chemistry, is what we're going to be looking at. Carbon has extremely rich chemistry and the backbone sort of everything we're going to be doing in this course. The few other elements you'll probably see frequently, hydrogen for sure, nitrogen, oxygen, those are all on the first 2 rows. Outside of the first 2 rows, we'll deal with the halogens, chlorine, chlorine, bromine, iodine, a little bit of phosphorus and sulfur, and maybe that's kind of it. Sodium, potassium, a couple of metals over there perhaps. So these orbitals that we find electrons in, we have s orbitals. These are spherical in shape, and basically all elements have some electrons in s orbitals. We have p orbitals as well, and I guess depending on, people always say that they're shaped like dumbbells, but I don't know. If you've ever seen a dumbbell, they don't really look like a dumbbell. Peanut, maybe looks a little bit better. So p orbitals are another possible type of orbital. Hopefully you guys remember this from first year. There are 3 different types of p orbitals within each shell. And they look exactly the same, but they're oriented in different directions. We call these px, py, pz. And beyond that, you can have d orbitals and f orbitals as well. But I don't think there's ever going to be a point in this course that we're going to be dealing with d and f orbitals. S and p is going to be where it's at in this course. And why? Because first 2 rows of elements only have S and P, and those are the elements we're going to be focusing on for sure in this course. It doesn't mean that other orbitals don't exist or they're not important in other areas of chemistry, or that they're not important in organic chemistry way down the line. But for organic chemistry 1, S's and P's are mostly what we're going to be dealing with. So orbitals come in different energies. They go from low energy up to high energy. You may remember seeing a diagram that looks sort of like this. This is a diagram which helps you determine the ordering of the orbital energies. So if you follow the arrows from the top down, the lowest energy orbital is 1s, and then coming down with the second arrow is 2s, then it goes 2p, 3s, 4p, 3p, 4s, 3d, 4p, 5s, and so on. Okay. So you remember probably doing this in the beginning of first year, maybe first semester, and then we use those energy orderings to work out electron configurations. Remember electron configurations? We get into nitty-gritty detail with these in first year, where we, this is just listing out all of the atomic orbitals for an element and how many electrons there are in each of those orbitals. And then we get into the exceptions, like chromium, I think, is an exception. And we're not going to get anywhere near that level of detail with electron configurations. All I need you guys to remember with electron configurations is that they exist and that all of the elements we're going to be dealing with come with a certain number of electrons that we could spell out with their electron configurations. So the electron configurations for some of the elements that we're going to be dealing with most in this course are listed here: carbon, nitrogen, oxygen, hydrogen, fluorine. Okay. Hydrogen, you see there, only has a single electron in its 1s orbital. The 1s orbital is the only orbital in the n equals 1 shell. So hydrogen, to have a full shell, needs 2 electrons only. All the other elements on this page to have a full shell need how many electrons? Any guesses? I'm sorry if people are answering online. I can't hear you yet. So if you're in the second row, okay, then to fill the n equals 2 shell, you need to fill the 2s and all the 2p orbitals. Because there's 2 electrons in the 2s, 6 electrons in the 2p, you need to have 8 electrons to fill the n equals 2 shell. Okay, and this is the basis of a rule that we talk about a lot in first year called the octet rule. Octet rule means that for an element to have a full shell, it needs 8 electrons. Except for hydrogen, because it's not in the second row, it's in the first row, it only needs 2 electrons to fill its outer shell. And because elements typically don't have, noble gases have full shells, but none of the other elements here do. So what they need to do is form bonds to fill their outer shell. Sounding familiar to most people? It's hard for me to read your expressions with the masks on. I understand the importance of them and everything, but yeah. Sometimes the black ones are funny too, because at a glance they look a little like a beard. These atomic orbitals, remember something called hybridization. This is where we take the atomic orbitals and we add and mix them together to make what we call hybrid orbitals. And this helps us account for the shapes that we see for organic molecules. I realize this is pretty surface and it's going through what took us months in first year quite quickly. And the idea that I want to get across is if there's material here that you haven't seen before, or if you have no idea what I'm talking about, you need to go back and shore that information up for yourself. Okay, it's going to be very important as we go forward. So for hybridization, what we notice is that if you look at just plain old atomic orbitals, okay, the S's and the P's that I talked about before, They often don't account for the shapes that we see for molecules. So we invoke this idea of hybridization, where we take atomic orbitals and we put them together and we come up with new combinations of orbitals. So in the example you see on this slide, we have a picture of methane, where if you take the 3 p orbitals for carbon and you take the s orbital for carbon, you can add them and subtract them in different combinations and come up with 4 new orbitals. We got rid of the initial 4, the s and the 3 p's. We come up with 4 more that we call sp3 orbitals. And they're called sp3 because they've taken an s and 3 p's and mixed them together to make these new 4 orbitals. So that kind of looks like this. We have a picture here of the orbital energies for the carbon atom on the left, where you see there's the 1s, which is in an inner shell. There's the 2s and the 2p's, which are in the outer shell. What we can do is take those 4 top orbitals, the 3p's and the 2s, we're going to mix them together, we're going to hybridize them, combine them, and you end up with the picture that you see on the right, where we have 4 orbitals that are all the same energy. All 4 of them are sp3 orbitals, and we've gotten rid of our atomic orbitals. We've traded them in for these new hybrid orbitals. And this allows for carbon to make additional bonds. It can make 4 bonds now, and it allows carbon to adopt the angles, the 109.5 that we see experimentally. It says these 4 orbitals are degenerate. Does anyone know what degenerate means? What would you say if your friend called you a degenerate? Yeah, stupid or not fully developed, I don't know. That's not what it means here in chemistry at all. Degenerate has a very different meaning. Degenerate in chemistry means equal in energy. Okay, so these 4 orbitals, but when we say that these are degenerate, we just say they're at the exact same energy as each other. So we can do hybridization where we take 1 s and 3 p's and make sp3s like we just saw. The other option is if you take an s and 2 p's, you can make orbitals called sp2s, plus we still have the other p left over. So you always have to have 4 orbitals. If you start with 4, you end with 4. So if you take an s and 2 p's, that's 3, the third p is still left behind and still available to make bonds. sp is the third kind. That's taking 1s, or the 2s orbital, and 1 of the 2 p's. Blend them together, you make 2 sp orbitals, and then we still have 2 p orbitals we didn't use in the hybridization, so they're still behind as well. So you'll have 2 sps, a p, and a p. All right, so if you take methane, CH4, perhaps the simplest organic molecule that we know of, we take the carbon and we're going to hybridize it. We're going to take the carbon's orbitals, the 3 p's and the 2 and the s. We combine them together and we have 4 sp3 orbitals that you see in the picture down here below. Each one of those orbitals looks sort of like this. It kind of looks a bit like a p, but it's lopsided. There's a big lobe on one side, a small lobe on the other side. And what we can do then is take each of these orbitals that each has 1 electron in it, and we can overlap them with the s orbitals of the hydrogens. We overlap these. Those overlap makes what we call a covalent bond, and we have our molecule. Okay, so we can, and more in this course, more perhaps so than you've done in first year, we're going to be thinking about bonds in molecules as being overlaps of orbitals. Many times I'm going to be bringing up hybridizations of atoms. So ethene, here's an interesting example. Here's a molecule with a double bond. So if you have a carbon that has 1 double bond, the hybridization on that carbon is sp2, not sp3. sp3 means the carbon has all single bonds, all 4 single bonds. 2 singles and a double means that it's going to be sp2, and I'm going to show you what that picture looks like here. Carbon atoms overlap with each other with these sp2 orbitals. Those are the gray orbitals in the middle that are overlapping to make a single bond. We call that a sigma bond because the bond runs along the axis between the two atoms. Also, you see those blue orbitals that are p orbitals. Those are the leftover p orbitals we didn't use when we did the hybridization. Remember, we had two p's and an s to make sp2. We still have these p's left over. They overlap sort of above and below the bond, the single bond, to make a second bond or a double bond, which we call a pi bond. Now, this distinction between a pi bond and a sigma bond is also going to be extremely important in this course. Everything I'm saying is extremely important, right? If it wasn't, I wouldn't be saying it. But the pi bonds are especially important because pi bonds are weak. If you look at this, look at this picture, these pi bonds kind of look like they're not pointing in the right direction to overlap. It's kind of this weak side-by-side overlap, these p orbitals. That means the overlap actually isn't fantastic. That means that the bond is going to be relatively weak. So what we often find is pi bonds are weak in organic chemistry, sigma bonds are strong. So it's one of those things that I can do if I look at a molecule and I see a double bond in it somewhere. I look at it and say, that double bond is going to be where the reaction is going to happen. That's the weak part of this molecule. Typically, molecules will react where they're weak. That's actually an important thing industrially when people are making food for packaging and they want to put it on shelves. Food will decompose, it'll break down. Fats especially, they'll go rancid if you leave them go too long. That's because of oxidation at double bonds. So to preserve food, to make food last longer, they subject it to a process called hydrogenation. And hydrogenation gets rid of the double bonds, which is making those molecules prone to reaction. We'll see lots of examples like this in the course where intelligent people who really understood well the chemistry of different things are, using that knowledge to change compounds, make improvements, and make useful products. Ethene, also called acetylene, C2H2, is one more example. This is a compound where the carbon has a triple bond and a single bond. And when you have carbons that have a triple and a single, we say that these carbons are sp hybridized. So remember, the carbon had s, p, 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 px, py, pz to start with. We're going to take two of them, the s and one of the p's, mix and match them to make two sp orbitals, and we still have the original p orbitals left over. So the two carbons here, the gray orbitals coming from the carbons, are the two sps pointing in opposite directions. The two p orbitals that are left over, you see there's the vertical ones, the blue ones, and there's also the yellow ones. The blue ones overlap with each other to make a pi bond. The yellow ones overlap with each other to make a second pi bond, so that in acetylene, this triple bond is actually a sigma bond, which is strong between the two carbons. And then there's two weak pi bonds on above and in front and behind. And I have another picture of the same thing. This is just sort of showing the overlap. So there's one pi bond, which will be a red and blue set going vertically. There's another pi bond, which is the red and blue set going in and out. Okay. So I'm going to be asking you guys lots of questions later on. The behavior of carbon atoms will change a lot depending on if they're sp3, sp2, or sp hybridized. Those are basically your three options for carbon in an organic compound. So I need you guys to very quickly be able to look at a chemical structure and tell me, is that carbon sp, sp2, or sp3? Okay. And I'm going to show you how to do this, and I want you guys to get good at it. What I need you to do is look at the atom and count how many groups there are around the atom. This is true for any element, but almost always it's going to be carbon that I'm going to be interested in. Count how many groups of electrons there are around the atom. A group can be a single bond, it can be a double bond, it can be a triple bond, or it can be a lone pair. Actually, in weird cases, technically it can be a single electron as well, but those will be not very frequent. If there's 4 groups, then it's going to be sp3. Like methane is CH4. CH4 has 4 single bonds, that's it. 4 groups means sp3. Ammonia is NH3 with a lone pair on the nitrogen. That's also 4 groups, 3 bonds and 1 lone pair. That's also going to be sp3. If there's only 3 groups, it's going to be sp2. This would be something like the ethene, like if there's a carbon with a double bond and 2 singles, that's 3 electron groups total. That's going to be sp2. And if it's sp2, there's got to be another p that hasn't as well associated with that atom. It's always 4 orbitals. Okay. And then there's 2 groups. If there are 2 groups, like in carbon dioxide. In carbon dioxide, you have a double bond from carbon to oxygen, and then a second double bond. Only 2 groups around the carbon. It's sp, and it must also have 2 other p orbitals in addition to those sp hybridized orbitals. Great. That was like a super quick refresher of orbital hybridization. Very important. One thing I'm going to mention just before I jump to the next slide is, you know, you've been receiving probably lots of emails from myself, Terry Gullen as well, about lab, about this course, about various elements of this course. If you're receiving the email, it's important for you. So even if it's coming from Terry, if she's sending the email, that means to both sections, it means it's important information for both sections. So one piece of information that came out last night that I just wanted to mention was what we're planning to do with office hours. Because we're actually discouraged from hosting, like what we used to do is just have a 3-hour block where students could pop into your office and ask you questions, and that would be that. They don't want us meeting in person now, and because it's sort of weird for me to have like a 3-hour block of time online with the camera open, I don't know. So what we're doing is 3 times a week, both myself and Terry are going to be hosting sort of an open 30-minute session, which is going to be kind of like a tutorial, where it's going to be on Teams. For me, it's going to be Monday, Wednesday, Friday in the half hour immediately after class. First one starts on Friday this week. Okay, so what that means is when you're done class, 10 minutes after class is over, find yourself a place to sit down. We're going to open up Teams, and I'm going to help do problems or anything along those lines that people would like me to do, answer questions. And Terry is doing the same thing, and she has a different time slot. I think hers is 11:30 to noon. And you can go to either one. You can go to as many or as few of those as you want. Okay, they're meant to sort of reinforce concepts that we're doing in class. If you feel like you're fine, don't worry about those. If you want one-on-one help, if you don't want to go to those sessions or you want something different, please just email me and I'll make a one-on-one appointment with you. I'm very happy to do that. I have lots of time I can give to you guys, and online people too. So yeah, just please take advantage of that. If you have any questions at any point too, just please feel free to ask. All right, we're doing great. Valence electrons are the electrons that we are concerned with bonding. These are just the electrons that you find in the outermost shell. So for carbon, we don't care about the 2 electrons in the 1s orbital because they're in an inner shell. They don't participate in bonding. Only the outer ones participate in bonding. For carbons, those are the electrons in the 2s, or for any second row element, they're the ones in the 2s and in the 2p's. Noble gases, as I mentioned, already have a full outer shell, so they are not reactive. But all the other atoms do not have full outer shells just on their own. So Lewis theory, and Lewis back in 1916, he proposed that atoms that don't have a full shell already, which is basically everything except the noble gases, they will share pairs of electrons with other elements so that all the elements in the molecule will have a full outer shell. So this is the idea of a covalent bond. And the picture here is hydrogen. Hydrogen just has a single electron in a 1s. It doesn't have a full outer shell. It needs 2 electrons to fill the n equals 1 shell. So 2 hydrogens come together. They each bring 1 electron to make one bond. And that's why hydrogen doesn't really like to exist on its own, but would much rather form a bond with another hydrogen. It's kind of like a potluck, right? Everyone brings something to the meal, and at the end, everyone eats well. You see a picture there of G.N. Lewis. He died in his research lab, and I think it's questionable whether he killed himself or not. It's not clear, but what he was doing was something probably most people would consider pretty careless. He took a gas form of cyanide called HCN, and he cooled it down into a liquid, and he tried to do reactions in that liquid. And his graduate student, whose name was Michael Faraday, who became an important chemist in his own right, came into the lab one morning and saw his supervisor dead on the floor of the lab. And he had known what his supervisor was trying to do with this solvent and everything, and put 2 and 2 together pretty quick, and realized as well, like back that, those are like in the 1920s, I think, that this happened. They didn't have the nice ventilation that we have in our new current labs over in Elliott. So he recognized that if he walked in there and this stuff becomes a gas quite easily, it's very volatile, he could just breathe it in himself and die too. So what he did is he ran into the lab with his nose plugged, he smashed all the glass out of the windows in the lab, and then ran back out. So we did this all in like 30 seconds, and then he called for help, maybe 911 or whatever the equivalent would have been in the day, because he wanted the room to air out. He wanted this gas to escape the room first. So that's what happened to Lewis. Thank God in chemistry now we have modern safety procedures and all that kind of stuff. Your risk of dying has gone down quite a bit. So Lewis structures. We draw Lewis structures. There's a procedure to draw Lewis structures. It's critically important, if I didn't say this enough already, that you guys are good and quick at drawing Lewis structures, and that you do it correctly. And that you can do all the stuff that goes along with Lewis structures, such as assigning formal charges, determining molecular shapes, determining hybridization, which we just talked about how to do. You count the number of electron groups around the central atom. Bond angles, you need to know those all as well. These are all things that we spent a lot of time on in first year, and those tutorials that are up on Acorn hopefully can bring that back for you guys if you're not already good at that. What happens in organic chemistry is often there are some shortcuts that you will start to maybe recognize pretty quick that you can take when making Lewis structures. First of all, hydrogen, fluorine, chlorine, bromine, iodine always make one bond. Oxygen, and usually sulfur, not always, but usually sulfur, makes 2 bonds. Nitrogen makes 3 bonds. Carbon makes 4 bonds. And if you remember how many bonds each of these can make, it's almost like Lego. You put them together in a specific way, and if the number of bonds works out, then you have potentially a good structure. This is okay, but I'm going to ask you not to rely on this overly strongly and abandon our procedure, because we're going to be looking at some weird examples where oxygen doesn't have 2 bonds, where carbon doesn't have 4 bonds. And if you rely on a simple set of rules like what's on this slide, it can lead you to a bad place, a dark place. So if you follow the procedure that's up on Acorn, it will work every single time. But you need to be quick. You can't be having sheets where you're looking up rules as you're doing it. You got to be able to kind of quickly draw these structures. Carbon can never have more than 4 bonds to it. And I'm going to probably write this on half of the people's papers in this class. Now that I say that, I don't know how, if I'm going to be writing on any papers, but carbon, when you be very careful when you're drawing your Lewis structures not to end up giving carbon more than 4 bonds. 4 is the absolute max for carbon. We have this thing called the octet rule. Carbon's not allowed to have more than 4 bonds. It can have less than 4, and we will be looking at lots of examples where carbon has less than 4 bonds, but it can never have more than 4. We sometimes call carbon, if it has more than 4 bonds, a Texas carbon. It's kind of this idea like everything's bigger in Texas, even carbon, but it's not real. So yeah, always 4. Triple and a single, 2 doubles, a double and 2 singles, or 4 singles. Electronegativity is important as well, that you guys understand the concept of electronegativity. So basically, electronegativity is the propensity, if that's the word to use, of an element to draw electrons close to itself when it's making a covalent bond with another element. It's how greedy that element is for an electron pair. The concept of electronegativity, I often think of it a little bit like if 2 people are lying next to each other in bed and there's a blanket covering both people. I kind of think as the 2 people lying next to each other are like the 2 elements in a covalent bond, and the blanket over them is kind of like the pair of electrons that they're sharing. So if you're in bed with somebody, you should share the blanket, but often what happens is middle of the night you might wake up shivering. One person has the blanket wrapped around themselves and the other person has no blanket, right? So there's the blanket hog and then there's the person that doesn't have as much blanket around them. So I kind of think of a polar bond as being like that. The electronegative element steals the electrons and wraps itself with these extra electrons, leaving the other element in that covalent bond bare. So the one that's wrapped with extra electrons that it took from its neighbor, it will have a negative charge or a partial negative charge. The one that's lost those electrons will have a partial positive charge. And if you have a partial positive and a partial negative, you'll have a dipole, you'll have a polar bond. The periodic table that I show you in this picture, you can see that the elements in the top right-hand corner of the periodic table, in red especially, these have the highest electronegativity. These are the most electron greedy of all the elements. Fluorine tops the list. Fluorine is a small atom, but it's very, very greedy for electrons. The ones around it, you can see chlorine, oxygen, nitrogen are also quite electronegative. And then as you move further and further away from fluorine, electronegativity falls off. Carbon is not especially electronegative. And anything lower than carbon, we often call it electropositive, meaning it would rather give up its electrons and take positive charges than have extra electrons around it. So let's take a simple molecule like HF. HF is a very interesting molecule. If anyone watches Breaking Bad, I think that was the plot of episode 2, season 1. Where they attempted to dissolve a body using HF. Anyone watch Breaking Bad? Yeah, a few people. It's a good show. Anyway, in the show, spoiler alert, but HF ends up dissolving the tub as well. Makes a bit of a mess. HF is an unusual molecule compared to HCl, HBr, HI, which are all hydrogen halides. HF is the only one of those that's not a strong acid. But what we have is HF. It's simple enough. We have a single bond between the 2 atoms, which is a pair of electrons that's shared. And that allows each of the 2 elements to have a full octet of electrons. Well, hydrogen doesn't get a full octet, right? It gets a duet, I guess. But fluorine, because it's much more electronegative, draws that pair of electrons in close to itself. And so what you see in the middle picture is the electron pair is drawn between the elements, but it's much closer to the fluorine. And so we use this little delta plus and delta minus symbol on the fluorine to show that the hydrogen has a partial positive charge and the fluorine has a partial negative charge. Delta, whenever we use that symbol, it means part or partial. Carbon dioxide has 2 polar bonds, but because of the shape of the molecule, because it's linear, those 2 polar bonds exactly cancel out. Okay, so we would say that carbon dioxide has polar bonds, but it has no net dipole. The molecule itself is nonpolar. So again, this is bringing back, hopefully, great memories from first year chem, all this Lewis structure stuff. Electrostatic potential maps is potentially something new, but we're not going to spend too much time on these things. Electrostatic potential maps are basically another way of visualizing molecules. It's basically the surface that's put on the outside of the molecule, and it's colored to indicate what the charge felt at that point would be. So if it's blue, in this example, blue means it's got a positive charge, red means it has a negative charge, and it's useful when you have large molecules for identifying the areas of positive and negative charge. So you may see this from time to time in the course or later on in other courses. Formal charges is one more thing, and this is covered as well in the online tutorial refresher on Lewis structures for you guys. Formal charge is basically a way to calculate charge for a completed Lewis structure, which is important that you're going to be able to do it. It's equal to the number of valence electrons the element has on its own, just based on its position on the periodic table. Subtract from that the number of bonds that it's making. Okay, double bonds count as 2, triple bonds count as 3. And then subtract from that the number of electrons that are unshared. Basically, the number of electrons that are in lone pairs. And this will give you a number. Formal charges are optimal when they are equal to 0. Okay, some atoms, you can't help it, are going to have positive or negative formal charges. Almost always, it's going to be +1 or -1. If you ever see a +2 or -2, you probably have a mistake somewhere in your structure. Generally speaking, a minus formal charge should be on an electronegative atom, like oxygen. And generally speaking, a positive formal charge, ideally, is on a not very electronegative atom, if possible. I realize the time. I realize it's 9:20. I just want to do one quick example before we go. Hybridization, we talked about looking at a Lewis structure and determining the hybridization of elements. I have a picture of a structure here, and I have it drawn out where there's CH, that's a single bond between carbon and hydrogen. You see there's double bonds. You see all the lone pairs here are drawn in as well. What I'm going to do is ask you, actually that's a different question. Ask you to label the hybridization of every carbon in this molecule. Does that sound like it would take a long time? When I'm done with you guys, you're going to be quick. You're going to go sp, sp2, sp2, sp3, sp3, and just be able to buzz through the molecule super quick and identify for each carbon what the hybridization is going to be. Okay? So right away, I would say any carbon that has a single bond, 2 single bonds, and a double bond are going to be sp2. So you can see on the left-hand part of this structure, there's this ring, this 6-element ring, 6-carbon ring, that's alternating single bonds and double bonds. Every one of those carbons is sp2. And they're all sp2 because they all have 1 double bond and 2 single bonds to them. On the far right, you can see there's a triple bond. If carbon is making a triple bond, it's sp. So you can see the 2 carbons on the far right are sp. There are 2 other carbons that make double bonds in this molecule. There's the one with the carbon double bonded to oxygen, and there's the one with the carbon double bonded to nitrogen. Both of those are sp2 as well. sp2 means 1 double bond, 2 singles. And all the other carbons are sp3. If they're all single bonds, they're sp3. Okay. What about some other elements? What about the nitrogen here? How many electron groups are there around the nitrogen? Electron group is a single bond, a double bond, a triple bond, or a lone pair. There's 8 pairs of electrons, but not 8 electron groups. There's a double bond, there's a single bond to the other carbon, and there's a lone pair. That's 3 groups all together on the nitrogen. That means the nitrogen is sp2. The other piece is that if it's a terminal atom, and this almost never will come up, but terminal atoms don't hybridize at all. So the oxygen that you see at the top, technically it has 3 electron groups, and we might be tempted to say that oxygen is sp2, but actually we would just say not hybridized. By terminal, what I mean is there's nothing else bonded to it. It's the end of the line, right? There's no other atoms bonded to it except the carbon chain that it's bonded to. That's right. So for the online people, the other oxygen that's down below is not terminal. It has 2 bonds going to that oxygen. It is hybridized, and it has 4 electron groups. It has 2 bonds and 2 lone pairs, 4 electron groups, which makes it sp3. Okay. So make sure you guys get good at counting electron groups and determining hybridization, and you'll get quick. All right, we're gonna close this up now. I'll make sure the technology hopefully is working better next time, although I did test it today too, so I'm not sure what's going on. But yeah, thank you everybody, and we will meet again on Friday.
Thank you.
Thanks.